This is part 10 of the Module 9 lecture. In this part, we're going to look at an example of pair samples and how we do the inferences for this case. So we're going to follow the same procedure that we've been following all along to test a hypothesis. And in fact, what we're going to do is going to be reminiscent of what we did in Module 8. All right, so the example that we're going to look at is the case of this multimodal training of children with mild autism. And this research company claims that this training increases the IQ of these children by 20 points. So in this situation, a researcher wants to verify this claim. And for that purpose, this person selects 31 children with mild autism at random. Then the IQ of these children before they start is evaluated. And then after they have been subjected to this multimodal training, then their IQ is measured again. So the results of the sample are given to us as the difference of the IQ after minus the IQ before. And the average of those differences from the sample of 31 children is 19.7, and the sample standard deviation is 2.35. Now, it's important to notice that in this type of problems, you have to be careful on how the difference is created, because the research could have equally have said that the difference is the IQ before minus the IQ after. So you need to track how the difference was calculated, because this is going to be important in the interpretation of the results. All right, in this example, they also want, in this example, they want us to use a significance level of 0.1 to determine if the researcher's claim is correct, and they want us to calculate a 90% confidence interval. All right, so what we need to do is then summarize the information. So we know that the mean of the difference under the null hypothesis is 20 points. The number of differences in the sample are 31. The sample mean of the difference is 19.7. The standard deviation of the difference is 2.35. And the significance level that we're going to be using is 0.1. Now, to establish the null and alternative hypothesis, then you can go back to the statement of the problem, and you see that the claim is that this training causes the IQ to increase by 20 points. It's not saying more than 20 points or less than 20 points. It's simply saying 20 points. And this person, the researcher that's performing the experiments, just wants to determine if that is the case or not. So that tells us that the null hypothesis is that the mean of the difference is 20, because that's what the claim is. And the researcher wants to verify that, so that the opposite hypothesis is that the mean of the difference is not 20. So from here, we can see that this is a two-tailed test with a significance level of 0.1. Now, the second step is select the distribution to use. Again, this is a random sample, so we can say that the 31 differences that we have are independent. The population standard deviation is not known, but we can estimate it with the standard deviation of the differences, and the sample standard deviation of the differences. And because the sample size has 31 differences, then we can assume by the central limit theorem that the sampling distribution of d bar is normal. So with all these three conditions, we can see that we are justified in using the t-distribution with degrees of freedom equal to the number of differences minus 1, and that is 30 degrees of freedom. Then in step 3, we calculate the test statistic, where we take the sample mean of the differences, the bar observed, minus the mean under the null hypothesis, which is 20. We divide that difference by the standard deviation of the differences, which is 2.35, and divide that standard deviation by the square root of the number of differences, 31. If you conduct this calculation, you find that the value that t observed is minus 0.7108. All right, now that we know the value of the test statistic, we can look at the critical value approach to find the rejection region, or rejection regions, because this is a two-tailed test. So then we use table 5, the table of t probabilities. We use alpha over 2 because this is a two-tailed test. So that's 0.05. And we know the degrees of freedom is 30. So looking at the table 5, look at the row 30 degrees of freedom with the probability of 0.05, and then you find that the t-value is 1.697. And of course, this corresponds to the upper critical value. But remember, this is a two-tailed test, so we have another rejection region on the lower tail of the distribution. Then we can use the symmetry of the t-distribution, and then we can see that the lower critical value is just the same as the upper critical value, but with a minus sign. So the rejection region then is if the t-observed is less than minus 1.697, or the t-observed is more than 1.697, then we reject the null hypothesis. Now, if you decide to follow the p-value approach, then to find the p-value, we know that the t-observed is negative. So, and we go into table 5, look at the row for 30 degrees of freedom. But remember, these are our values on the right tail. So they are positive because they're on the right tail of the t-distribution, which is centered on 0. So, but for the same probabilities, you have the exact same values on the left tail, but now they are negative. So what we do is we compare this negative t observed to the values on the table, but they're negative values. So with that in mind, then if you look at the row for 30 degrees of freedom, you see that the t observed of minus 0.7108 is larger than the largest negative t value, minus 1.310. So again, make sure that you look at the t table and look at that row of t values and change the sign to negative. And you're looking for the t observed and see how it compares to those negative values. And you will see that this negative value of the t observed is closer to 0 than the largest, the largest value on the table, which is minus 1.31. So, and this value minus 1.31 corresponds to probability of 0.1 on the left side of the distribution. And this implies that the p-value is larger than 0.1. If you rather calculate the exact p-value, you can use Excel. Here's the formula, and you will find that the p-value is 0.4827. All right, now we have the critical regions. So here are the critical values. Then we have we know that the p-value is larger than 0.1. Then with that in mind, we see that the t observed of minus 0.766 is larger than the t critical of minus 1.697. That is, this value lies in the non-rejection region, and also the p-value is larger than an alpha of 0.1. So, based on these two criteria, we can decide that the null hypothesis is not rejected. So that we cannot say that the mean gain in IQ because of this training is 20 points. So, we interpreting this decision, we can say that there is not enough evidence to reject the claim that the intensive multimodal methodology training increases the mean IQ of all autistic children by 20 points at a 0.1 significance level. All right, so based on the hypothesis test, all we can say is that the mean does not seem to be different from a gain of 20 points in IQ when this training is applied. So a good alternative or a good complement to the hypothesis test is to calculate the confidence interval, in this case, a 90% confidence interval. So then with alpha over 2, because the confidence level is 0.9, so alpha is 0.1, divided by 2 is 0.05. And we know that the t distribution we're using has 30 degrees of freedom. Then if you go to table 5, you find that the T alpha over 2 value is 1.697. All right, with that value, then we use these formulas that we have for the upper and lower confidence interval limits, and then we plug in the sample average, the T alpha over 2 value, the standard deviation, and we divide that by the square root of the sample size. If you carry out those calculations, you find that the lower confidence interval limit is 18.9837, and the upper confidence interval limit is 20.4163. All right, what do these numbers tell us? So we can say that at a confidence level of 90%, the mean gain in IQ of all children with mild autism after the multimodal training is between 18.984 and 20.416 points. And we can say that there is a gain because the difference is positive. And remember, we're using the difference, if you go all the way to the beginning, we're using the difference of after minus before. Since the difference is positive, that means that IQ after is larger than the IQ before. Then we can say that based on the confidence interval, that there has been a gain in IQ by applying this training to these children with mild autism of 18.984, between 18.984 and 20.416 points. Okay, with this, we complete this example where we're using paired samples. So in the next section, we will talk about comparing the proportions of two independent populations.